Good morning. Thank you for attending my talk. So for many people, quantum computing is very theoretical. So this talk, the goal of this talk is to go deeper into the practical perspectives of quantum computing. So we'll talk about different topics, the basics, of course. Then we'll talk about the quantum computing simulators if you want to experiment by yourself. And now we are lucky enough to have free quantum computing cloud services. So you will be able to do your own quantum computing computations on the cloud. And we will talk about different topics around cryptography, how to reverse cryptographic primitives. There are basically two ways to do that. And we'll see examples about CRC8 and AES, right? And then we'll finish with the post-quantum cryptography to see what are the solutions for the future. But first, let me introduce myself. So I'm Renaud Lifchitz, coming from Paris, France. I'm a security expert working at Digital Security, which is a subsidiary of the Econocom Group. My main interests are mostly security of protocols and number theory. That includes cryptography, of course. But let's start first with the basics of quantum computing. So I'm pretty sure you know a few basics. So this is to remember you the basics. So first, small-scale objects like atoms, molecules, photon, electron, and so on. Both behaves as particles and waves during experiments. It depends the way you measure them. If you measure them like particles, if you want to have a position, for example, they will behave as a particle. If you want to measure a frequency, or if you want to measure a power, they will behave as a wave. So it depends how you measure them, actually, right? Another interesting topic about quantum computing and quantum physics in general is the main characteristic of these objects are not defined when they are created. Everybody thinks a particle has a position and a speed. It's not the case until you measure them actually. When you create a particle, when the particle is created first, it has no position and no speed. It's when you will measure it that those figures will get defined upon measurements, right? So what we say actually is that they have a probabilistic position and a probabilistic speed, for example, or a probabilistic frequency. And once you measure them, this probabilistic function will collapse into a single value, and their actual position and speed will get defined at this point. So this is the third point. So consequently, it's not possible to measure some physical properties of a particle and then copy them into another one. It's not possible. It's the no cloning theorem, and you can actually prove it because it's a theorem. And strangely, you can take these properties into account and define a way to do powerful computations. Even if this seems constraints, you can use these constraints to do a lot of powerful computations. So how does it work? In traditional computing, you use bits as information. In quantum computing, you will use qubits, that is to say particles that can be 1 or 0, like bits, but that can be also a combination of 0 and 1, a superposition of 0 and 1, because the particles can behave like 0 and 1 once they get measured. So when they get measured, they will have a fixed value, but before they will behave like they are at the same time 0 and 1. So when you will do computation, with that kind of qubits, they will take all their possible values. So you will have all the possible results at the same time at the end of the computation. So that's very powerful, of course, because when you have a growing number of qubits, you have a huge field of results that gets computed at the same time, virtually. The difficulty will be to focus on the result and find the interesting results in all the possibilities, right? So in a mathematical point of view, a qubit is a vector of two values. For example, the qubit ket 0 is 1, 0, and the qubit 1 is 0, 1. And they form a basis from a mathematical point of view. That is to say, every qubit is a linear combination of 0 and 1 with different probabilities. That can be 100% 0, 100% 1, or a combination of both. That is to say 50-50 or 20-80 and so on. There are ways to combine qubits to form what is called qubit registers using tensor products. So that's very mathematical. So don't be afraid of that. It's not a major point. But the easiest way to visualize a qubit is to take a sphere, what is called a block sphere, and say the 0 qubits is like an arrow in a unit sphere that points to the top, and the 1 qubit is an arrow that points to the bottom of the sphere. That is to say, they are opposites on a sphere. And on a sphere, you can rotate the vector on basically every axis. That is to say, you can rotate the vector over the x-axis, over the y-axis, or over the z-axis. And quantum computing is actually exactly this, only rotations around the 3 axes. So once you visualize this, you are able to do any kind of quantum computation just by rotating the vector around the 3 axes, right? What's interesting in quantum computing is that for thermodynamic reason, a quantum gate, what is a quantum gate? It's like a gate in traditional computing, that is to say a AND gate or OR gate or XOR gate in traditional computing. You can have exactly the same thing with quantum gates, but they are a bit different because quantum gates must be reversible. Why? Because when you compute in a given environment, your environment is very fragile. You cannot have any kind of modification from the external environment. So your environment should be completely closed, completely isolated from the outside. So you cannot have any kind of energy going in or going out your environment. So for thermodynamic reason, you cannot have any energy that is consumed or that is fueled outside. So that way, your system does not consume any kind of power during computation. So the computation is completely reversible. So for example, in traditional computing, you have the AND gate. The AND gate, you have two inputs and one output. But of course, this is not reversible because from the output, you cannot guess the previous 2 inputs. In quantum computing, you will be able to do that because basically every single quantum gate is reversible because of thermodynamic reason. You cannot have any kind of energy coming in or out from your environment, so it's completely reversible. So every gate that is reversible will be a quantum gate, basically. Okay? So let's see a few examples. It will be more easy for you to understand. The easiest quantum gate is the X gate, that is to say, a gate rotating the qubit around the X axis. And we have seen, if you rotate the 0 vector around the X axis, you get the 1 vector, the 1 qubit vector. If you rotate it in the opposite way. So this will be a rotation around the X-axis, and the gate who does the rotation is the poly-X gate. That is to say, it's similar to the NOT gate in traditional computing. You get the opposite qubit. When you input 0, you get 1. When you input 1, you get 0. It's completely similar to the NOT gate. And it has a matrix, you see, that is the normal matrix rotated at 90 degrees, sorry. And if you apply 2 times the poly-X gate, of course, you come at the initial point, so it gets cancelled, and you have the identity gate, which does nothing, right? Another interesting gate is the Hadamard gate. The Hadamard gate actually transforms any fixed qubit, for example, the Ket0 or Ket1 qubit, into a superposition, an equal superposition of 0 and 1. So this gate will be fundamental and will be very important because it's basically the gate you will find at every input circuit when you are doing a quantum computing circuits. Because this gate will enable you to do parallel computation over all the possible input values of your circuits, right? So it transforms a fixed qubit like 0 and 1 to a superposition of 0 and 1 with exactly the same probability. So you get half of the time 0, half of the time 1. And you can use it to initialize your inputs to do parallel computation on a set of qubits. Another useful quantum gate, because we have seen quantum gates with only 1 input and 1 output. So this time, the CNOT gate will be very useful because it's the simplest gate with 2 inputs and 2 outputs. And basically, it's a if-not gate, okay? That is to say, it has 2 inputs, the control gates and the control qubits and the target qubits. And it basically tests if the control qubit is true. And if the control qubit is true, it will negate the target qubit, right? So basically, it makes if the input is true, then negates the target qubits. And if the input is false, do nothing, right? So the symbol is that one, a small plain circle and a large empty circle, right? And it tests if the first qubit is 1, and if the first qubit is 1, it will negate, apply the poly-X gate to the second qubit. It's the CNOT gate. And when you have multiple CNOT gates, that is to say, a CNOT gate with many control qubits and only 1 target qubit, that is called Toffoli gate. And Toffoli gates are universal. With Toffoli gates, you can basically program any kind of traditional gates, like AND, OR, XOR, make additions, make tests, and so on. A simple gate also is the swap gates that only swaps 2 qubits. So that's very easy to understand. And when you have sufficiently enough gates, you can have a universal set of gates. That is to say, you will be able to combine them to give you any kind of circuit you want, any kind of circuit that does arithmetic operation, that does algorithm, that does everything, okay? So Toffoli gates only is a universal set of gates. If you only have Toffoli gates, you can manage to do everything in traditional algorithms and any kind of function, right? But generally, it's easier, to have a set with Hadamard gates, phase shift gates that makes a rotation of the phase, that is to say the z-axis, and controller node gates. So that's the case on basically every quantum chips available now. So we will use 3 or 4 different gates to manage to have any kind of circuits. Anyway, there are some difficulties with quantum computing, because you cannot copy a register into another. That's the no cloning theorem. Or better said, you cannot copy them in an independent way. When you copy a register into another register, they will get linked. And they are magically linked, right? You cannot have an independent copy like in a program when you set A equals B, where you simply copy the value of B into A. So that's not very possible in the quantum world, right? Of course, you don't have that many qubits in quantum chips because they are expensive and because you need to protect them from the outer environments, and it's quite complicated to have many independent qubits protected from the environment. So usually you compute with only a few dozens qubits, not more. So that's the current records nowadays. And you can have errors, of course, if your environment is not completely protected, okay? You can have some false measurements, okay? Some errors in your computation, so you better use error correcting codes in order to ensure your results will be good. How many qubits do you need for serious purposes? It's estimated by the biggest, like IBM or Google, that you need 50 qubits only to have a sufficiently powerful computer, that is to say, a quantum chip that is able to be more powerful than the computers we have, the traditional desktop computers we have. Only 50 qubits will be enough, because you will be able to do many kind of computation and many kind of results explored at the same time. That's basically 2 to the 50 power. That's 10 to the 10 to the 15 or 16 possibilities at the same time, only if you have 50 qubits. That limit is called the quantum supremacy, because when you will reach this limit, we will definitely prove that the quantum chip is more powerful than the traditional chip, right? And of course, you need quantum gates and qubits with a good fidelity, that is to say, a few errors when you measure them. Currently, the error rate is about 1%, so you have 1% chance that you have an error during a gate or during a measure. That's pretty good, but not enough for serious computation, because when you have multiple gates that are chained, and if you have only 1% error rate, when you chain more than 40 or 50 gates, you will have 50% chance that you have an error in your computation. So for serious algorithm, you will have an error rate that is quite important. So 1% error rate is not enough really to do serious things. The most important thing to remember is the number of qubits is not the most important factor, right? The most important criterion. The most important criterion, in my opinion, is the qubit fidelity. That is to say, if we have a good fidelity rate, we will be able to have a deep circuits, that is to say, interesting algorithm to run on. It's not a matter of number of qubits, actually. So let's have a look at the different quantum computing simulators you can find. All of them are free, so you just have to create an account and you can play with them. So the first one is Quantum Inspire. Quantum Inspire is quite a simple one, okay? You can either drop your gates on a partition, like this, and experiment, or enter the gates in an assembly listing, an assembly source code, where you apply successively the gates, like the AND gate, the CNOT gate, the poly-X gate, like an assembly program. So either as a source or as a circuit, as a graphical circuit. Another one is Quirk, from the algasser.com website. Quirk is one of the most advanced because you can find all the arithmetic operations like the addition, the multiplication, the division, even the exponentiation. So you have high-level primitives in arithmetic, so you can do a lot of things. And the author has been employed by Google because of the success of his tool. Quite interesting tool. Then the author is working at Google now. And if you want to play on the go, in the subway, on the train, and so on, you can have a small simulator on your Android phone. That is to say a quantum circuit simulator, which is called QCS. You can design and simulate any kind of simple circuit with a smartphone and have the different probabilities, the different measurements you see here. So, for example, let me show you, with Quirk. Yeah, Quirk here, right. You see here, right. So this is Quirk. You have the input qubit here, so 2 input qubits. Let's apply an Hadamard gate to the first qubit. So, as I remember, the Hadamard gates will make the first qubit a superposition of ket 0 and ket 1. So equal probabilities of 0 and 1 for the measurements, right? And if we apply a CNOT gate after the Hadamard gate, right? Remember, the CNOT gate is when the first qubit is true, then negates the second qubit, right? What happens? So if you simulate with your brain the circuits, so the Hadamard, you will have half a probability to get 0 and 1. So let's assume it's 0. If you have 0 here, the CNOT gate will do nothing, okay, because the first qubit is false. So you will have 0 and 0. Let's assume the Hadamard gate gives you 1. Then the CNOT gate will negate the second qubit. So you will have 1 and 1. Okay, so either 0 and 0, either 1 and 1. Okay? And this is exactly what is said here. You have 50% chance that you have 0, 0. 0% chance that you have 0 and 1. 0% chance you have 1 and 0. And 50% chance you have 1 and 1. So you can see here, both qubits will have the same value, even if we don't know the value in advance. Okay? Now, let's negate one of the qubits with a poly-X gate, right, at the end. And you see now you will have 0, 1 or 1, 0, half the time. Okay? And that's interesting because that was a big problem for Einstein. Einstein called that kind of circuits, which is called the EPR, the paradox. He called that a spooky action at distance, because if you have two different particles that exit from these quantum circuits, and you put them very far away, one from the other, for example, at the opposites of the universe, right? They both behave at the output of the circuits as particle and wave, so they both have the 0 and 1 value. But when you measure one, you will instantly fix the value of the other because they have opposite value. So when you measure 0, you will be sure that the other at the opposite side of the universe will be 1, and conversely. And Einstein was very worried about that and called that spooky action at distance. But you cannot use that for communication because you cannot choose the value 0 and 1. It's just a matter of probability, and you cannot transmit any bit of information like this. Right? If you want to experiment with more simulators, you have a very exhaustive list on Quantiki Wiki. So you can have a look at that one. But that's more funny to experiment on real quantum computing hardware. And now we are lucky enough to have nearly 5 quantum computing public services. All of them are free. You just have to subscribe, but you can use them completely freely. One of the first I demonstrated 4 years ago was the Bristol University Quantum in the Cloud, which is a photonic quantum circuit with only 2 or 3 qubits. So that's quite limited, but that's one of the first, and that was interesting to trace, to test, and to experiment with. Now we have much better one. The Chinese have launched a service around the brand Alibaba that gives you up to 11 qubits. IBM, which is one of the well-known players in the area, gives you up to 14 qubits for free. And if you are a paid customer, you can have 20 qubits. Rigetti, which is a competitor, gives you up to 19 qubits, and even more than 100 qubits if you're a paid customer. And the last one is D-Wave. So you probably know D-Wave, but D-Waves is a bit different, because D-Waves is another quantum architecture. You cannot implement directly quantum gates, but you will be able to create a circuit that will mostly do optimization problem that gives you what is the worst value of a function, the higher value of a function or the lower value of a function over a wide range. So basically it's for optimization problem, numerical optimization problem. That is to say, for example, if you want to enhance your finance portfolio, you will be able to do that kind of numerical optimization using D-Wave. And D-Waves claims that it has 8,000 qubit chips, but remember that is not a universal quantum computer, but just a network that do problem optimization, right? And it had been proven recently that both kind of architectures are equivalent. That is to say, you can make the same circuit using a universal computer or an adiabatic computer, but you will need much more qubits in an adiabatic computer because it's less efficient for general purpose computation. Now let's talk about cryptography, because it's a very interesting area for quantum computing. We hear a lot of things in the media about breaking cryptography with quantum computing. So what's the actual situation? let's see first how do we implement basic p-box operations, that is to say basic permutations. P-box is a permutation, is a basic brick for many symmetric algorithms, right? So how do you model permutations using a quantum computer, sorry? Basically, if you have a complex permutation, first you have to decompose the complex permutation in single permutations, that is to say, in 2-qubit permutation, because basically you can decompose any kind of complex permutation in single permutation, in a composition of single permutation of 2 elements. Then it's easy when you have permutation with only 2 elements that to apply them swap gates. Swap gates is just a permutation of 2 elements at the same time. So you replace all the permutation of 2 elements with swap gates. But a swap gate is not a gate that exists for real in a quantum architecture. So you have to choose gates that are implemented in hardware for real on quantum architectures. And one of the most basic gates that will help us is the C0 gate, remember? And basically you can replace any swap gates here with 3 C0 gates that are opposites, like this. With only 3 C0 gates, you get a swap gate. So you can implement basically any kind of complex permutation with only C0 gates quite easily. And you can even simplify the whole circuit at the end, because if you have opposite C0 gates, they get cancelled at the end, so you have a much more simpler circuit. Right? So it's quite easy to model any kind of permutation. And it's kind of magic, because every single gate, remember, can be reversed because of thermodynamic reason, right? So if you want to do the inverse permutation, you just have to execute the circuit from the end to the beginning, and you will have the inverse permutation very easily. So there is no need to think about the circuit and do the same for the reverse circuit. You just have to execute the circuit the opposite way, and you get the opposite permutation. So that's very, very simple with quantum computing, because basically you have only reversible computation, right? So that's the first way to reverse a cryptographic primitive. You implement the direct function, the direct operation, and you just read the gates in the reverse order to apply the reverse function on a given result. But unfortunately, not every function is reversible, right? So it's not that easy all time. And sometimes you want to reverse complex functions that are not completely reversible. And the other solution will be to use an oracle. An oracle is a black box saying yes or no, depending on if the result is interesting for you, to select good values among a lot of different values, find the values you are interested in. So that's basically the 2 different approaches to reverse any kind of cryptographic primitive. The easiest oracle that exists is the Grover oracle. The Grover oracle, you just have to implement the normal function, and then to implement a black box saying yes or no. Is it interesting for me? Is this value the good value among the other? If you combine your function with the Grover oracle, you will be able to find the right value very efficiently. For example, if you have 10 business cards in your pocket, how many search you have to do in average to find the correct one? Tell me. 5, yeah. That's half the number of business cards you have in your pocket, because you have basically 50% chance to find the right business card when you have reached half of your business cards. So the complexity to find one business card among 10 business cards is five operation on average. That is to say it's n complexity, because it will depend on the number of business cards you have. But basically, you have the same amount of operation than the amount of business card you have in your pockets. So that's not very efficient. Grover Oracle does a lot better, because Grover Oracle will do the same among unsorted business cards with only the square root of the number of business cards you have. So if you implement an Oracle saying if the name of the business card is Lifchitz, for example, if you have my business card in your pocket, you will find it in only the square root of 10 searches. That is to say, basically 3 searches, and not 5. And the optimization will be better if you have a lot of business cards. For example, for 100 business cards, you will find it in only 10 tries, and 50 if you have to classically find among all the business cards, right? So Grover Oracle is very efficient if you have to find a value over many, only with the square root of n and not complexity of n. So as an example, I have modeled a simple function you probably know, which is CRC8. So CRC8 is not a cryptographic function, but is a hash function that's not that easy to reverse without studying the mathematical properties. CRC8 or CRC16 is used, for example, in the zip archives to tell you that it's not corrupted or corrupted during the storage or the download of the file. It's used in integrity purposes. So if you use, if you model the CRC8 function very naively, you will, for example, find this solution, right, which use only C0 gate, but you have a lot of them, right? 9, 12, 15, 18, 21, 24. With 24 C0 gates, you can model the CRC8 function. But the problem is you have temporary qubits here. You need 8 qubits for the input, and you have 8 qubits in the output. But the problem is that you will use 8 temporary qubits, so you need twice the amount of qubit of the function. And you will not be able to reverse the function because you don't know the value of the temporary qubits at the end. If you want to find the input, you need to have all the qubits as the output, and you don't know the value of the temporary qubits in the output to reverse the full circuits. So that works, but only in the normal side, not in the reverse side. Because of the temporary qubits that are called ancilla qubits. And it's a problem here to reverse the function. So in order to have something better, I've used the Lifchitz framework. Lifchitz framework is a useful framework to do reversible computation. And with this framework, you are able to input truth table with input and outputs. And this framework will find you the optimal, if it can, optimal circuit to do a given reversible computation. And we are lucky, the CRC8 function is a reversible computation. So with a few minutes of computation, you can get this circuit as an assembly listing that is optimal. You cannot have less instruction to do the same things. It's completely optimal. And it's also optimal because it uses no temporary qubits, no ancilla qubits. So you only use 8 qubits to do computation on input of 8 qubits and have results over 8 qubits, right? It's completely optimal. Here is the same circuits, but much more in a graphic fashion, right? So the idea is to here set the outputs of the CRCH circuit. You have the reverse CRCH circuit, and at the end you will get the input value of the CRCH function. That is to say, you have reversed the CRCH function using quantum computing. And what's interesting is you haven't studied any arithmetical property of CRCH. Huh? It's a generic way to invert function. You don't have to study the mathematical properties of functions. It's a very general way to invert the function. So this is with Quantum Inspire. And if you do the simulation here my output is 0. Here it's 1, 0, 1, 0, 0, 0, 0. I do the reverse CRCH circuit. So at the end, I will have the input of CRCH that gives you as output 0, 1, 0, 1, 0, 0, 0, 0. And when you simulate the circuit, you will have 100% of time the good solution, which is 1, 0, 0, 1, 1, 1, 1, 0. Well, that works. Now, if you use not a simulation, but a real run on a quantum chip, you will have a bit of noise here. So sometimes you will find bad solutions, but most of the time, like 90%, 92% of the time, you will find the good solution, right? So when you do quantum computation, it's useful to do many tries to keep the solution that is here most of the time to cancel the noise, right? For example, on IBM quantum chips, the number of tries by default is 1,000. So you get the circuit executed many times, and you find the major, the first. You keep the first results, and you cancel the other. Here's the full program to run the function on IBM quantum chips, IBM Q experience, on real quantum hardware. So you need the IBM Q14 Melbourne quantum chips, which has 14 qubits, right? So you have the full program here. You have to send to the batch queue of the quantum chip the program, and when it gets executed, you query the results, and you have this kind of results. So you have the different tries with the number of counts, and you see the good results among the first top results. And you see there are bad solutions. For example, 0, 0, 0, 0 is the solution with the highest number of counts, 95, but it's not the solution. It's a solution with the lowest energy, 0, 0, 0, 0. So it's the first one, but it's not the good one, okay? So you have a few mistakes, a few errors because of the decoherence of the quantum computation. Right? What's interesting is when you put this kind of circuits in a simulator here, so this is the reverse CRCH circuit, you can set as the output a superposition of outputs and find what are the inputs for that superposition. For example, here, it's 0 and 1 at the same time on the first qubits. Here, it's 0 and 1 at the same time, and here also. So basically, you have set 8 different values at the output, and you ask for the different possible inputs, right? And you see here something that is very interesting here. So it's 50-50, 50-50, so it's not interesting, but here you will see that this qubit is always 0. So you will have the reverse computation of 8 different circuits at the same time, and see this qubit will be 0 all the time, this qubit will be 0 all the time, right? So you can find interesting properties of function like this. We can do the very same than the P-box modeling with the S-box modeling, right? For example, if you take the S-box function of AES, which is a bit more complex, but this is a basic substitution, right? And I have found a good substitution with quantum gates. So it's very small because the quantum circuit is quite complex. It's not only 14 gates here. It's 281 poly-X gates, CNOT and Toffoli gates, right? It's not optimal probably, because the circuit is not simple. So this is the simplest circuit for the S-box of AES, but it's probably not optimal, but this is one of the best I've found. I've tested all circuit up to 14 gates, so the optimal circuit must have at least 14 gates. And it's a good thing that there is no simple optimal circuit, otherwise AES will be broken, okay? You can do the very same with XOR encryption, okay? To break XOR encryption, you have to reverse the XOR encryption, so it's very easy to reverse XOR because it's its own inverse. But you can use an oracle to test the higher bits of the results to see if there are printable characters. Printable characters in the ASCII tables will have all their upper bits set to 0. So this will give you a strong condition to reverse a XOR function using a Grover oracle. Left as an exercise for you, if you want. So what are the threats against actual and current cryptography? The main threat for symmetric cryptography will be Grover algorithm, as we have seen, which is a square root of n complexity. So Grover algorithm will be able to divide by 2 any kind of symmetric algorithm, divide the key size by 2. So for example, if you use AES 128, it will give you a symmetric encryption with an actual strength of 64 bits, which is broken because 64 is the current record for a broken symmetric encryption. So Grover algorithm will divide by 2 any kind of algorithm, any kind of key size for symmetric algorithms, right? So the solution is to double all the key size. If you have a symmetric encryption, if you use a symmetric encryption, you just have to double the key size and you will be safe because we can prove that Grover algorithm is optimal and there is no stronger algorithm that will find the key faster. So we can prove that is optimal. So if it's optimal, you just have to double all your key size and you are safe. It's not that easy with asymmetric encryption because with asymmetric encryption there exists a much stronger algorithm which is polynomial this time, not in square root, but polynomial. That is to say that grows only with the number of digits of n and not with n directly. And it's able to break any kind of asymmetric encryption in polynomial time, and it's called the Shor algorithm. And it breaks basically RSA, DSA, ECDSA, ECDLP, basically any kind of asymmetric encryption we use nowadays for web browsing, for certificates, for SSH connection, and so on. And it uses a quantum Fourier transform algorithm, which is similar to the Fourier transform you use when you do signal analysis. So there is no easy way to protect against this kind of threats. The best way to protect is to use post-quantum cryptography, which is a very new field. And post-quantum cryptography is the kind of encryption you can use to protect against quantum computing. So if you have a look at the website Qubit Counter, you can find the current number of qubits, the current record we have. So now it's 128 qubits for the Rigetti quantum chips, but you can have a look to track the change and the effort in the quantum computing race. And if we graph the number of qubits over time, it looks like a Moore law, exactly like in traditional computing, because the number of qubits is doubling every year or every 18 months. And you see it's growing very fast. So the threat is coming. To avoid these threats, there are basically 6 different kind of algorithms that are supposed to be strong enough not to be threatened by quantum computing. So 6 different approaches: lattice-based cryptography, multivariate cryptography, hash-based, code-based, super singular elliptic curve isogeny, and of course the symmetric encryption is strong enough to resist to quantum computing if you double all the key size. So you have 6 different families of cryptography you can use instead of the current asymmetric encryption. And you have a conference that is called PQ Crypto if you're interested in these topics. And it's the 10th edition this year, and I think it will be in China. And you can follow their Twitter feed to be informed. They don't have a fixed website, but it's a very very strong area of research at the current time, right? There are very few post-quantum cryptography algorithms. The most well-known for the moment is NTRU. It's a lattice-based cryptography algorithm. And you can use, for example, NTRU encrypt if you want to have asymmetric encryption, and NTRU sign for digital signature. Right? So thank you for your attention. We can take 1 or 2 questions in the remaining time. Any question?
No answer questions?
Everything was so clear.
Hello, I have a question. As we all know that CRC8 is a kind of hash functions. So what do you mean by using quantum computer to break?
Can you speak a little bit louder?
Okay, sorry. Yeah. I mean that the CRC8 is a kind of hash functions. So what do you mean by breaking the CRC8 using quantum computers? Yeah.
For CRC8, breaking is basically reversing, finding an input on a given output.
The input can be very long, not just 1 byte, right?
I'm sorry, I don't hear you. Can you speak louder? It's noisy in the background.
Okay. Yeah. I mean, you have a very long input, right. And I can use the CRC8 to get a 1 byte result.
Here is the basic CRC8 function, that is to say that takes 1 byte as an input and gives you 1 byte at the output. So that's the simplest one, but CRC8 can be extended to take much larger inputs, yeah. But here the demo is only with 1 single byte because of the current capacity of quantum chips.
Okay, I see.
It's just a demo that works for the actual quantum chips, but we don't have enough power now to have much larger inputs.
Okay.
Only you can simulate it, but you cannot run it on actual hardware.
Another question about the D-Wave. We know the D-Wave is quite different from the security implementation of quantum computers. So what does the number of qubit in the D-Wave meaning? Is it like the qubit numbers in the security implementations?
Sorry, I think I haven't heard the whole question.
Yeah, we say that if it's a security implementation of quantum computers, there is a number of qubit. We use this number to to show how strong this computer is. But in D-Wave, it's quite different from the security implementations. And it said that it have 1,000 quantum qubits. So so can we use this number to compare with the security implementation of the security?
I'm not sure I've heard you. It's very noisy in the background, so I suggest we talk outside and it will be much easier. No.
Okay, sorry. I will discuss with you after that.
It's lunchtime, so it's noisy in the background. Speak loudly, please.
Sure. So thanks for your talk. I had one question about that reversing hashing functions. I presume if there is two possible inputs for the same output, you would get both inputs with 50% probability, for instance. But what would happen if there is no inputs at all? For a given output byte, there is no possible input that would generate it.
Interesting. It depends if the circuit is reversible or not. It depends. If the circuit is not reversible, you will use temporary qubits, ancilla qubits. So you will have solutions, but with impossible temporary variables. Otherwise, you probably won't have any solution. That is to say, only noise. But it will depend on the circuit, and it will depend mostly if you have an optimal circuit, that is to say, absolutely no ancilla qubits during the computation. Thank you for attending. I will be available outside for other questions. Thank you.